We'll start from talking about yesterday's problems. Well, not yesterday's, but the problems of the previous contest. Today we're not going to cover all of the problems. For instance, I still have some misunderstanding with the solution for problem J, so we'll leave it for tomorrow. And tomorrow we'll cover this problem, and for all other problems you had trouble with, we'll have a brief discussion, and after that we'll move to another topic which is prepared for the day. So let's start with problem C. In this problem you had to count the number of non-isomorphic trees with a degree not more than 4, and the main problem was that you were going to count non-isomorphic ones, so if you could permute like the numbers of those vertices, the trees are supposed to consider it equal. So first you can come up with the idea that it's a little bit easier to count rooted trees. So once you get a fixed root, you know, even after the applying renumeration of, well, isomorphic checking the root, if the root still will be the same, then we can kind of start from the root, and after that we'll count just the number for the subtrees with just dynamic programming, where we will store the only size of this tree and combine the outputs for all subtrees to collect the number of ways to construct the whole subtree. And so how exactly would we guarantee that isomorphic trees would not be counted twice? So it is pretty common for counting the isomorphic trees. You can always use a bracket sequence or use some hashing, and the main point about counting not isomorphic things is that if we are going to combine our tree from some subtree 1, subtree 2, subtree 3, that we don't want to consider several permutations of these subtrees as different combinations which provide different trees. They should be considered only once. So it's easy when those things are all not equal. You can kind of know that even if you would count them for each permutation, you kind of know what will be the number of such permutations. But sometimes they could be equal. For instance, if you know that in this subtree here will be one subtree of size A and 3 subtrees of size B, you know that these are going to be different from all of these because these have different size. But among these ones you could have equal ones. So actually, instead of counting what would be the number and multiplying it for all subtrees, instead of that you want to only pick 3 of them, and you do not care about the order. So instead of just multiplication, you will get the formula for instance, for 3 subtrees, it would be like that. And if, in general case, if you have k subtrees, this formula will be like that. So to count actually for all subtrees, you want to fix the size of the subtrees, and after that fix size, actually the amount of the subtrees of this size, which would be inside this subtree, count for one particular subtree, count what is the number to choose several of such subtrees, and after that proceed with another size. And of course you should guarantee that this size would be different. So I usually first fixing like the largest size and counting the number of ways, and after that I'll do for the smaller ones. For in this problem, since you have the degree only maximum would be 4, so you can try like this size and this size, but if the degree could be a bit larger, you also would like to use a dynamic programming here, so you probably will have to add additional parameter like what is the current size which we are considering. So first you're trying to put several subtrees like some maximum size, after that you're decreasing the size and trying to add some small subtrees, and the equal ones should be always appear only inside one size. So it's kind of independent for subtrees of different size. And yes, I forgot to say that that was when we were counting the rooted trees. But actually it is not very hard to change the problem without root to the problem with root, because you can define as a root a center of the tree. It can be like either the center of the diameter of the tree, or it would be better, I think, for this problem to pick a centroid. So centroid is a vertex or an edge, so that all its subtrees has size smaller than half of the size of the tree. So you would pick a centroid as your root because it's always unique. It's either a vertex, or in this case it is an edge. And in case if it's an edge, you can kind of just pretend that it's a vertex of degree 2, and you would make this vertex a root and calculate everything considered this vertex as a root. So I saw several teams solve this problem, so I think this topic is familiar to you, so maybe if someone has some questions, or otherwise we can just go ahead.
What is this?
It's a binomial coefficient. You want to pick you know that in your tree that you want to pick several subtrees of equal size, and for each one you will know what is its number of ways to construct the smaller subtrees, and after that you want to pick k from them, and the sequence are like considered equal if you can permute them to equal ones. So instead of multiplication, like number of ways to make this subtree multiplied by number of ways to make this subtree multiplied by this is not correct, because it counts different permutations several times. You actually want to only count it like a set, not like a sequence. So you know the formula. This formula is also usually written like this. it's the number of ways to pick A items from the set of size B, which is equal to this. Oh, Ash, it's actually a little bit different, so I wouldn't write it. So, did I answer your question? Okay. I saw that a lot of teams have trouble with problem G, but I don't think it's very hard and very much to discuss about it. It was just about considering cases. So you could have like sequence of points, and you have to split all those points into two arithmetic progressions. But it wasn't just a sequence of numbers, it was a sequence of pairs. So the idea was just to try to pick what would be the one of the progressions and try all those points that are fitting into it, and after that just check for the rest of the points. And actually you can try all ways to construct one sequence just from several points in the beginning. So it is either you have that the first two points are in the one progression, then you can just find out what the progression is and try for all other points if it fits into this progression. It is the other case if it's the first one with the third. And I guess that's all cases, only two cases have to be considered. And of course, these cases also have some sub-cases when the progression is like for x or for first coordinate or for the second coordinate, and once you found like what are the fitting points, you should also to consider very carefully what would be the second progression, but I guess it's like only everything about the careful consideration of all the cases. It's nothing like theoretically specific or hard. So I guess we will not stay for long this problem and go ahead to the next one. Problem Ash was about the nurses. I don't know, was it clear from the statement or not that to check whether if you can replace this vertex, it can always be done if there is a path from any non-special nurse to this one. So I guess for the single nurse it's very easy to check. And about the pair of nurses, you might notice that there should be like two passes from two different non-special nurses to the pair of special nurses, and the passes should not be intersecting by the vertices, right? Because if they're like intersecting, it means that we have like two pairs are going to, the pair of nurses are going to replace the one, which is not actually how it works. So even if we have two which can replace this one only can replace someone, only one. So in this case it's kind of obsolete, and we only should check for two non-intersecting passes. And finding two non-intersecting passes, it's very common problem. It can be solved by the flow algorithm. Just if we were caring only about non-intersecting passes by the edges, we would just draw a net like this and check whether the maximum flow one with the capacity is 1 on all edges, and check whether the maximum flow in this net is equal to 2. But since in this problem we are caring about non-intersecting passes by the vertices, we have to split the vertex into 2 and make an edge of capacity 1, and just keep all incoming edges here and all outgoing edges here. This is also a very common trick how you can provide additional restriction to your flow network, that each vertex should be used only once, or like some internal requirement for the maximum amount of flow you can put through the vertex. So that was the main idea, and how you actually solve it in the square time. So we want for every pair of special nurses check whether the flow in this net is 2. So we will just fix the first pair, and we only looking for one pass. And after that we looking for the net after we pushed one pass to our flow. So if we will use one of the most common algorithms for looking for the maximum flow, we would, after using the edges, we'll make the backward edges instead of them, and we'll continue looking for the passes with considering these edges can be cancelled. So we only do this iteration one time for only one node of the pairs, and for all other candidates for the pair, we will not run the search independently. We'll just use one like dfs or bfs to check what vertices are reachable in this net. And if you found that this is also be reachable after we put one pass into our net which goes to the listeners, and we also can reach this one, which means that it will be possible to push the pass which ends in this vertex, which also means that listeners can be replaced along with this one. And you can notice that the actually order of which pass we are looking, the first one, it does not influence the result. So if we had this problem, we can either find this pass first or this pass first, and it does not influence the possibility to find the second one. So you can always fix the first node and put the pass independently from the other element of the pair, and for the second node you can only check without pushing any edges. So it's like for n candidates for the first nurse and better v candidates for the first element. E is the time you would spend for looking for the first pass and pushing it to the net, and one more time is to check which vertices are reachable in the current net. And that's all.
It's like I only need to find the same pattern and check reachability.
Yes, yes. You only have to push the first path, and when you're looking for the second one, you only need to check. You don't have to like prepare for some further searching. You just have to check for which end vertices there exist best. You don't have to do anything about it after all. It's only check reachability, which can be done simultaneously for all vertices in one DFS. Okay, problem L. I can talk a little bit about this problem. So here you had queries like put some block of items somewhere, and you can also put it in between. So and the query is to check the number of distinct items on the segment. So first you can maybe already know by your experience that when you are going to insert some things between, so it's more likely that the data structure you are looking for would be like some binary search tree, and more usually the Cartesian tree is used for that. But also, again by experience, you can see that the constraints for this problem were like 30,000. So it's kind of obvious that authors suppose that you will use a square root optimization, some kind of data structure. So I guess in this problem would be the best way to use the second one. And one more thing about the specification of the query, that you have to find the number of distinct elements on the segment. This query is also pretty common, and you can little bit modify it. So if you have like the segment LR and you want to find the number of different elements, you making this transform. So if you had here like array A, you'll define the array B, or like is like the smallest G, so that AI equal to basically we just find the index of the next element, which is equal to the current one. And if you look to this array, so the query is just becoming from L to R. Count how many elements, like I, so that bi is greater than R. Is it clear? Why is it the same? So we can kind of define that the element is not unique if the index of the next one is somewhere inside the segment, and it's unique. Not unique, but it will be representative of this type if it is the last element. So to translate this problem to this one, it is a much easier problem for us. We can use like almost any data structure, like a usual set, to recalculate these values after each query. And when you look at this problem, it becomes a little bit clearer what to do. It just does not require some like operations with sets, but only with the numbers. I think this query is a bit easier. So when you would apply your square root modification, you will have like all your blocks will be, or like blocks, because I wanted to name the blocks or our parts in square root data structure. So consider like you keep several, I don't know, blocks here. Let's say that this would be the blocks, and this would be like buckets of items. So we'll have several blocks. Each would contain several buckets. So we'll try to make that the size of these blocks would be no more than square root, and the same the size of such blocks we'll try to keep no more than square root and asymptotically. And once we have like a query to insert somewhere, we'll just look at what block our queries points, and after that we can just manually insert it to the set, pick all the buckets and just attend to our list. But here we will have some additional data to keep to have ability to answer to our queries, is that we will have to, for our values b, I for each block, we'll try to store them in sorted order. So here we'll have some bi for each bucket, and for us to simplify the query of this kind, if we would have this bi's stored in sorted order, then we'll just use the binary search to find the bound where the unique one appears, and after that, like, use the partial sums to find what is the total, or not even my partial storage, we just only care about its size. So we just count the size of the set. And that's kind of everything you have to do. And obviously we only do it for a block which fully lies inside our query. And for these blocks which partially intersects our segment, we'll just manually try every bucket and check if it's like larger or smaller. So to put one bucket into the block, you'll have to resort everything. So I guess it's and like yes, it will be like square root 4 multiplied by log. And again, for the query, you have to use a binary search for each one. And how you actually providing that the sizes of the block is no more than square root and its number, because when you like put the bucket inside one block, it naturally increases its size. So every like and square root times of operation, you will be like changing these blocks. So if you just drop every block, and after that you reconstruct them from the beginning. So if you have like this block is smaller, this one is larger. So every square root of n operations, you will do reconstruction. So for everything, so just make them equal. Which will provide you that their sizes are always not larger than square root n. And for this kind of operation, you also have to like sort everything. So I guess the total complexity should be like this. I don't know if it's possible to remove the log or even solve it without the square root, but I had the solution with this asymptotics in the past. Pretty good margin of time. So I guess like the main point of this problem is that you want to use a square root optimization, and I think that this translation is also very useful for this problem, and not only for this problem, but like almost every kind of problem when you have to count the number of distinct elements on segments. I'd say like in every problem you can use it.
Sorry, can
Yes.
you repeat that translation you said about the query?
Sure. I'll show you by the example. So if you have you just, instead of keeping the key of the element, you store the index of the next one with the same key. And when you have to count the number of distinct elements in the sub-segment, you will only you would like, instead of counting what would be the set of the size of the set of the uniques, we'll only we'll have to look at these pointers and check the number of pointers that goes outside of the array. So which is like the number of elements which is larger than this number. Which is much easier, like if you have, when you splitted this array into buckets and sorted them to just binary search operation. Okay, so the problem K is the problem I was going to talk a little bit more about. So in this problem we had like polygon, and you had to split it into two polygons with the equal areas. So there are also several kind of ways of how you can do it, but I think I'll show you the one that it is easier to understand why it's working. And this one requires for us to find the triangulation of the polygon at the beginning. Do you know what triangulation is? It's when we split our polygon into triangles that like lie fully inside. And after we found the triangulation, well, maybe we'll better start with the triangulation algorithm itself. I suppose that probably someone does not know what is the best way to find the triangulation. Probably there are some people. So the algorithm looks as following. You can prove that there is always a triangle which you can cut out of the polygon. What does it mean that you can cut it out? Is that the triangle is made of the three adjacent vertices, and is that the inside area of this triangle lies fully inside our polygon, and there is no other stuff inside the triangle, like vertices or intersecting edges, anything. So such triangle always exists, and the algorithm is supposed to find such triangle. After that, it will cut it out and proceed with the rest of the polygon. So the first is how we are going to check whether the triangle is good or not. Can we cut it or not? It is just considering several cases. The main case is that, for example, like for this triangle, well, it is not just one. Like for triangle, it is clearly not good because it has a vertex inside. So for first we're going to do for triangle to check can we cut it out or not, is that we have to make sure that there is no vertex inside this triangle, and actually check whether the triangle containing a fourth point or not. There are also several ways how you can do it. The one is that you can make these three vectors in either clockwise or counterclockwise order, and you will have that this point is from the one side from each of the vectors, and to do so you can use the vector multiplication of this vector and this vector. And since maybe I'm willing to discuss the vector multiplication maybe later, I'll just keep the formula here. So when we're going to check whether the point is from the right and from the left, from this vector, we're going to use this formula of from this vector and from this one, and after that we're going to check the sign. So since this is clockwise order and this vertex is also from the right, so here we want to check that the sign is negative. So here sign will be negative, same as for this pairs of vectors, and same as for this vector and this vector. And if the point would be like somewhere outside, so clearly for this vector we'll have the different sign. And the second way how you can do it is just you're making the equation of the line, like you know if you know how to construct this equation, you just put the vertex inside the equation, and again, since if we keep the order, our directing vector of the line should be pointing either all outside, either all inside. And again, when you put your point into this equation, you want to check if the sign of the value of this expression is the same for all lines. That's how you can check. Again, it's very similar ways, but a little bit different. So okay, first you have done is that you make sure that the triangle contains no other points. And clearly you don't have to check any intersecting edges, because if your polygon have no self-intersection from the beginning, it would not have the case when there's some edge going through this triangle without any inside vertex. So you don't have to check for this case. And another case what you have to check is that this triangle is not an outside triangle. So this triangle is clearly not which we are going to cut from our polygon, because it is not inside our polygon. And how to check whether the triangle inside polygon or not? We'll just pick one point, maybe center, maybe something else, but I think the center is a little bit more smoother. after that you're going to check whether this point lies inside the polygon or not. Do you know how you can do it? If the polygon will be convex, then we could use just the same approach like with this triangle. But instead of like 3 lines, we'll have the end lines or vectors. But since the polygon is not convex, the way we're going to use is to draw a ray in some direction, and it is better to, like, not like better, but I usually use like a vertical ray, maybe somewhere here, and after that you want to count how many intersections with this ray does the boundary of our polygon has. And clearly, if the number would be even, this means that the point is outside the polygon. If it's odd, that it is inside. And one like a small case, how do you consider the case when we have intersection just matching some vertex of the polygon? So we do not want to carry this intersection as twice, because clearly like we intersect only once in the boundary. To avoid any bad experience in these cases, you just always consider your segments like the left point is included, the right point is not included. So when you will check the intersection from your ray with each of the edge, like for this one you should not count, and for this edge you should count. And basically how you actually check for intersection, you just have again the ray, you have that the left point should be from the left of our ray, and this point should be from the right from our ray, and in this case this is not strict non-quotient, and this is a strict comparison. And also like this point should be above. So it's also like a little bit another second thing that we have to check that this is actually above. And I guess there's no other way to check it other than finding the intersection itself. No, of course you can. Just for this segment, you want to check whether this point is from the left or from the right. Yeah. And here also you don't actually, here you can again use either the vector multiplication or you can construct this line and put into the equation your point. And here I guess you do not have to care about strict comparison or not, because if you like pick in the center of your triangle and you make sure that there is no other vertex inside this triangle, so you should like never touch other edge. So this check is you do not care about the strict or not, and for this you care because you want to provide that the left vertex of your edge is should be counted if it matches the ray, and the rightmost should not be counted. And if you check on vector, like if you have thing like this, which is like should be counted like a 0, intersections is a 2, so in this case it will be counted as a 2, and like it is touching with the right point, it will be counted as a 0, which both of us cases are working like intended, because we only care about reminder modulo 2. So this in this case will be considered like the number of intersections. Okay, so that's how you check whether the triangle is good. And once you can check it, for the first step is that for all triangles of our polygon, we're going to find the ones that we can cut out. So for each from the n triangles, we're going to perform all the checking, which also works in linear time. Because of the this check, you have to check all vertices, whether it's inside or not. Just down here. And this check, the second one I was talking, you have to check each edge count, like count intersection of the edge with our array, which is also n edges. So it requires n square time to find all the good triangles. And after that, you will just store your triangles maybe in queue. So we're going to cut them one by one. And after we picked some triangle and cut it out, then we have this vertex is removed from our polygon, and we can make these two vertices adjacent. So we're going to store the vertices of our polygon in some list with connectivity in both directions, so that after we remove this triangle, we have to check all the new triangles that appear. So after this triangle is removed, we have the new triangle, this one, to check, and this one, which clearly is not good, but this one is good. So after we removing this triangle, cutting it out, we have to check all the triangles that appeared after removing this point, which was only two candidates. And if there are some good ones, then we just also put them in the queue. And if it appears that when we are taking the triangle from the queue and it contains the point which no, that's not the case. This never should happen, or should. Yeah, actually, it also could be that when you when you take the triangle from the queue and remove, and if you already removed one of its vertices, then you just ignore and go to the next one in the queue. And this algorithm working in this way. So here it's just another thing. You have this number of the initial triangles, and during this algorithm you'll have to n some additional triangles to check when the polygon is reconstructed. And since it is the same asymptotics, so everything will work in square time. So that's how we found the triangulation. Let's go back to our program. Also, interesting thing about this algorithm of triangulation is when we found the triangulations, and like if we consider the triangles itself, and we connect the adjacent triangles, then the triangulation provided by our algorithm should make a tree on these triangles. If you have triangulation like this, then you would have this tree. So you're making a graph, a tree from the triangles with a connecting edge when the two triangles have the common edge in triangulation. So after the triangulation is completed, you will have like a tree of the triangles. And after that, so how we going to cut out the polygon from this. So let me draw a larger picture. So I'll draw the vertices just in the middle of the triangle, and it would be correspond to the vertices of our tree. First, let's consider that we picked some constant, for example, 1/2, and we're going to I'll just show you how we construct, and I think you will understand that how exactly the algorithm works. So we're picking some entering edge, for example, this edge. This would be the first edge, and from its middle we are counting C. Like we split this half of the edge in the proportion like C1 minus C. So this is C, this is 1 minus C, and we're doing the same here. So we have like the gate, and also draw these lines, and we'll just make this division of like all these edges. So like here we'll have this, here C, here 1 minus C, here again the C, here 1 minus C, here C, 1 minus C, and also for this edge, like for everything we'll just split the edges in this proportion. After that we'll connect the points like this. And here again we're making these edges, also dividing every edge in this proportion. We can point here, 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 and we connect like that. For each of this. Connect like this. And here it will be like something like that. As you see, we kinda cut out some smaller polygon from the center of our polygon, and the rest of the polygon is also a connected polygon. And the actual size of cutted out polygon is only depends from this constant of the relation that we picked from the beginning. So by adjusting by this constant with like a binary search, we can find the, well, it's clearly like monotonically increasing, since if we are taking the larger constant, then our internal polygon will be larger, and vice versa. So we can use a binary search to find this constant, which provides us with the internal polygon of the same area as the external. So we just and also I did not mention that after we like cut out this polygon, obviously we have to calculate its area. I hope you know how to count the area of a non-convex polygon, right? So you can just use this trapezoid method. So like, in this area, then removing this area and for every edge. So the main idea for this problem looks like that. We're using the triangulation to kind of define the structure of our polygon, and after that, once we've found like this tree of triangles, we are growing the inside, like the core of our polygon, which is a tree. We will like growing some meat on these edges, which we are going to cut out from this polygon. By adjusting the constant, we can find the appropriate size of such polygon. And probably here I drew some redundant points, so instead of this thing, we can just only connect immediately like this. And here also we can just connect like this. Here, just to decrease the number of vertices in our polygon. So I think we only have to do things like that when we do not have the edge in the triangle. So I guess the picture of the polygon can look like this. So this was a long discussion for the one problem. Does anyone have any questions? Yes?
The centers are the intersection of the medians?
It's I guess you can just take the average weight from the all three vertices, like arithmetic mean, and if I'm not mistaken, it will match the intersection of the medians. Yes. But you can just pick maybe intersection of anything else. It doesn't actually matter in this problem. So this problem was kind of opening to our today's topic. So I'd like to talk to you about some famous problems in computational geometry. So I guess the algorithm of looking of triangulation is also would be useful for you. Maybe some of the next problems would be familiar to you, so I'm apologizing if you would not see something new, but I hope that there will be something new in all my presentation. So the next problem I want to talk to you is we have a set of n points on the plane, and the problem is to find the pair of the most distant points by the Euclidean distance. You know this problem? And raise the hand who knows how to solve this problem, faster than in square time. Give you guys. Okay, it's fine. So I think it's not that bad if you will hear the solution one more time. So the first observation we have to do is that we only have to check the points from the convex hull. I hope the algorithms like constructing the convex hull are way too simple and common for me to explain. So we'll start with the convex hull, and we can kind of prove this fact, maybe, or just prove it a little bit. If you have, for example, two points which are not from convex hull, and you can choose a segment. So it would be if we just continue our line here and find the edge where it intersects the convex hull, it will be always not worse for us to pick either to move this point in either here, and the same from here. And here, we'll check, put this one, and it will be still better. So I know it's not kind of a very strict proof, so it's just for you to believe me. After that, we are supposing that we constructed the convex hull, and for each point we kind of wanted to find what would be the most distant. And the first mistake that you can face while solving this problem is that you cannot just pick one vertex and try to look for the most distant using binary search or ternary search, because clearly if you have a case like this, just almost any case, if you look like these 2 points, what would be the distance here? And if you put more vertices somewhere in between, then the distance will be decreasing to the middle of the edge and then again increasing. And the same for each edge. It will be increasing here and then decreasing. So by this function, clearly you could not find what would be the maximum of this function. So this way does not work. But the way which works, which I also will not prove strictly, is that to find the pair with the largest distance, you have to check not all the vertices, but we will check all the edges. So we take the edge and we constructing the line on this edge. And instead of looking for the most distant point to the point, we will looking to find the most distant point to the line. So we are looking for these distances. And once we find the most distant point, for example like this, we would check as the segment connecting this most distant point with both ends of the edge, and we'll check them for the answer. And the statement says that we always will find the pair of the most distant points by checking this edge and the point which is the most distance from the line on which the edge lies. And so yeah, I'll leave this statement without proof for now. Maybe in the end we'll have the time, we'll come back to this one. So we're going to check every edge and every line and find the most distant point. So how we're doing so? If we remember the formula for the distance between the line and the point, it will be like just we put in the point in the equation of the line, and just maybe we should divide it if the these coefficients are not normalized. So we have to normalize the line. So this may be not necessary. And in other words, we're just taking this vector and checking for the scalar product of this vector and just develop this point, or like vector from the zero, which is the same. And I think I've already told you that if we are looking at the scalar product with some, like, it doesn't matter which vector, for the all vertices that are making a convex hull, that the function of scalar product with this vector should have like some extreme maximum here, some minimum here, and it is increasing like from the minimum to maximum and decreasing from maximum to minimum. So this point we could find with binary search, and if you like use binary search for every edge, for every line, you'll check for this line. We'll have this point, and we will check this point with both ends of the edges, and we'll find that this segment is the longest. But actually, we do not have to use a binary search like in the problem, I guess, like B from the contest, not previous, but the contest was like 2 days ago. I said that if we are going to check, like find the maximum scalar product with some vectors, and if these vectors like are already will be sorted, like in our case, since we have the convex hull, we can just take the first edge, construct the line, just check all the points and find the maximum one, and when we are moving to the next line, we'll just look at the pointer of the current maximum and move it further while it is increasing the value of the scalar product. Just the same as in the problem D about asteroids. So actually, after we found the convex hull, the algorithm works in linear time. One time we're just looking for the maximum for the one edge, and after that, for each edge, we're just moving the pointer, which will also like rotate no more than for every point twice. Yes. Is it clear? Okay, so let's go to the next problem, and this time we imagine that we, from our set of the points, we're going to find the 2 points which are the closest by the distance. It's like the same problem, but instead of the maximum of the distance, we are going to find the minimum. Who knows this problem? Oh, of course, with the idea of solution of it. Yes, you know?
Maybe if we divide it
Mm-hmm. Mm-hmm. Yeah. So, anyway, I'm going to describe the algorithm one more time, since I will need it further. The idea works like that. So, consider we have some set of points. We are going to split the set into the 2 halves by, for example, vertical line. So we're looking for the line which splits our points into 2 parts. So just like if we sort all the points by the x coordinate, we're taking the median element and we just split the first half of the array here and second half of the array here. And after that we solve the halves recursively. So after we did it, we have the smallest distance like for this subset and for this subset. And of course we're taking the minimum of them as our current answer. So let's say that this answer is D. So now we're going to check if there are some pairs from different sets which are closer to each other, like with distance lesser than D. Let me read this. It is obvious that we do not care about the points that are larger than D from this line, right? Because it will take, like, if it will take more than D to reach this line, it's clearly that the distance to the point will be even larger. So from this line, we only keep like the strip of the wide D, and we only consider these points. And let us see at the list of these points and sort them like from the top to the bottom, like simultaneously. So this point, then this, and this, and this, and this, and this, and this, and this, like that. That will be this. And the only thing we are going to do after that is just for each point, for example, from the first list, we are going to check the next, I don't remember actually how many, I can say the next 3 points to this direction and the next 3 here. And the idea is that we do not need to check too far from this point, like somewhere really far here, because again, look, if we would need that, this would mean that, like, if we have a point here, we know that this segment is lesser than, no, we only care if the segment is lesser than D, right? This. And since the whole segment is lesser than D, then this is also lesser, should be lesser than t, yes, right? And if we have like this rectangle with this size is d, and this is smaller than d, then, and we know that there is no pair of points inside this rectangle which has the distance smaller than d, we know that the amount of points in this rectangle is very, very low. Like it could not be more than 5. No, we can just try. Like here is a d and a d, and we know that for each pair of the vertices, the distance is lesser than d. I guess it's like for 4 points, it's only possible when they are in the corners, and you cannot even put the 5th point into this rectangle to have to not have the pair of the points with the distance smaller than d. So we don't have to look at for the more than 4 points in the second list after this point and before this point. So we just like constant. So to actually solve the problem, once we have 2 parts recursively solved, we'll have like only to sort the points and to check with another cycle, like what will be the number of points which come to the strip, like could be, and like the size of the current set in the worst case multiplied by this constant, which is like 10 or smaller, and that's all. And I would say the most hard part is to sort the points. So if our iteration would look like with additional log, so the whole asymptotics will be multiplied by 1 more log just because of the divide and the conquer algorithm. But there's no need to sort the points in each iteration. Like when you are dividing them, you can just keep it like with sorted by the x, and like the second list when you will store the points in the sorted order by the second coordinate. And when you're splitting the sets, you can just not like you'll have these points sorted in the order by x, and you have will be just one more lists with sorted by the y. And after you are splitting, you can just take the points from this sorted order and to make sorted lists of the 2 components. So there's no need to actually make a sort inside each iteration. So this you don't need to put here. So in the end, you will have like only n log n time to solve this problem. Is everything clear? Okay. So one more problem. This one I will try to keep with all the proofs. So I'm pretty sure no one knows how. Maybe someone heard about the algorithm, and at least I'll provide the proofs to the algorithm. So the problem is, again, we have a set of points, and now we want to find the smallest circle that contains like or covers all the points. So, who does know how to solve this problem? You know, in what time? Expectedly. So you know the algorithm, and maybe you'll be interested in the proofs at least. I personally find the proofs for the algorithm the most entertaining thing. So first, I'd like to say that you can solve the problem like this by using like two ternary searches. You can just try all the centers, and the function will be obviously the largest distance to the point from the set. And you can just first try the first coordinate, then try the second one. So in like log at this time, where this log is like could be larger than log logarithm of n. So you can solve it like this. Just maybe this could just save you time if you are not looking for the best way of solving the problem. But the algorithm we are going to see right now, is also like solving it recursively. So let us define some function. F, where P is a set of the points which we are going to cover by our circle, and there is another set. Let's call it O, which contains some points that we have to contain on our boundary of the circle. So it will be clearer why do we need this second set for additional constraint. But like initially it will be like empty set. So just call our algorithm with this set as empty, and we'll just see what it provides us. So the algorithm goes as follows. So for example, we have some circle. Like initially it could be like any circle, any empty circle. And we will look at our points from our set P one by one. If the point goes inside the circle, then we're good. So we are counting this circle like a current optimal answer. So from our set P, we have considered like some prefix of points. We consider that the current circle is the optimal answer for this prefix. So initially the circle will be like with the zero size somewhere. And we are increasing like our prefix one by one, so we put in this point. If this point goes inside the circle, then clearly the circle remains the same. I had the answer for this set, and the answer for this set plus something would not be smaller. And since we've got the answer of the same size, it still would be the optimal. So if the point goes inside, we just skip and go further. But if it appears that our point is outside the circle, then look, here we have some P, some like PI, our current prefix that lies inside, and here we have the answer for this subset, for this prefix, and we have one more point which goes outside. Then we can prove that for the answer of this set plus this point will or should or will definitely lie on the boundary of our circle. Okay, let me prove that. So let's imagine that for the circle like this without our point, we have something like here. And let's see at the case where the answer for the all points plus this point does not contain this point on the boundary. So let me just show that this is never an optimal circle. Let's consider the process where like the one circle becomes another. So we are trying to like imagine the process where we can very slowly translate from the one circle to another. More clearly, it just we like define in the time from 0 to 1, and in time 0 the circle looks like this, and in time 1 the circle looks like this. And what would be some circle in the middle? It's just like its center will just split the segment between the centers in the relation t 1 minus t. So just like it goes with a linear speed, the center from the one center to another, and the same with the radius of the circle. It just linearly changes from this radius to this radius. So just imagine like one circle translates to another one. And in this process, the main observation is that the point that is has fixed position. During this process, the time when the point goes inside the circle is just a consecutive segment. So if the point goes inside immediately and the circle moved in some direction, then the point could only move out from the circle and never come back. And the same if the point is somewhere outside, then it can come in, and from time it just can come out and never come back. I think we can prove it's like very strict, but maybe we'll skip this just to save a time. So we'll skip this proof and see what it provides to us. Since if we have this circle is the answer for all sets without our point, and we imagine that there is a circle that does not contain this point, and still it is the optimal answer for the joint set, then we'll just try to slowly translate the circle from for the previous set to the current one, and we see that all the points that were inside from the beginning, they will be always inside, because in the end they are inside, and in the beginning it is inside. So we kind of could prove, if we come back to the thing I was talking that all points are always inside. And about this point, it is clearly would be the some moment of time where this point just get inside the larger circle, and it's clearly at this moment it would be on the boundary of the circle. So there would exist a moment of time where all points are still inside our circle, and the new point is appearing on the boundary of the circle, and the size of the circle would be smaller, obviously, because this is smaller, this is larger, and this is somewhere in between. So that's how we prove that if we had the optimal answer for all points without the current one, that if it is not going inside our circle, that it definitely should be lie on the boundary of the circle that would contain everything. And if we face this case, this would mean that we want to recalculate, construct another circle for this prefix. In this case, we will call our algorithm on the prefix, or joined with the current point. So let me just, it will be smaller if just one point, it will be larger if it's response to prefix. And then to the second set, we are going to put this point. And let's imagine that the algorithm will reconstruct our circle so that it will find the optimal answer for this prefix. Then we'll just continue, and in the end we'll have the optimal answer for the prefix equal to the size of the whole set. So we kind of understand how the first layer of the algorithm works when we do not have a point that have to lie on the boundary. And if we imagine that this algorithm works, if it can find the optimal answer for some set, if we know that some point is for sure on the boundary, then we know how to solve our initial problem. But we don't yet know how this algorithm works. And it only differs in one thing, that for this algorithm we've already proven that for some point we know that it should lie on the final boundary. So this, let's call this problem F1, and this problem is F2. So they are kind of similar. F1 uses F2 to solve itself, but we don't yet know how to solve F2. So now let's consider the problem F2. We have some point that always should lie on the boundary of some circle. It could be empty circle, circle like this, circle like this. And we have again a set of points that we should cover with circle, with this point lying on the boundary of the circle. Then we'll just we'll do pretty much the same, but we'll just initialize our circle like an empty circle around this point, and after that we again just trying to put some more points and try if it goes inside. Obviously, it's a very first iteration, we'll see that the point is not going inside, and we'll have to do something. But first, let's consider again the more common case. We, for example, have some circle with the point on the boundary, and we have that this circle is the optimal circle for some prefix of our this set. So consider F2 would be in and this point, like let's call it O1. And here we've taken some prefix of this set and we found the optimal circle. And again, we're having some point that does not go inside. Here again, we can prove that for this joint set of all these prefix points and the new one, even with the restriction that we know that this point should be on the boundary, we can prove that the answer for this set will contain both now. Well, we don't now actually prove that it will contain O1 because we proved it earlier. We on the previous step when we actually called this method. But now we can prove that this problem this point should also be on the circle of the optimal answer for all this set. So here we will use like the same proof. Like we have one circle with a fixed point, have another circle with a fixed point, and like one, but not like this. The point is the same. Here we can use like the same proof, but the translation will be a little bit more complicated because we have like one more point that should be fixed. But the translation is also would go like this. Maybe it will be a little bit like spinning, but still for all points that are inside which are inside from the beginning, they will be inside for every moment of the time. And in this way, we also can prove that once we have our second point goes inside, like then we would stop and we'll have the smaller circle than the circle that does not contain this point on its boundary. So when we see like this, that again we have like some prefix, we don't have the current point inside, then we'll have again like reconstruct. I will make the same picture like this. Here we know like for this prefix and for some point O1 we have the optimal answer, and for this point, if we add it, the optimal answer does not contain this point inside, then we can prove that the optimal answer for this prefix contains this point. And so since we only care about the circles that contains this point on its boundary, because we proved it somewhere earlier that for the answer for like some other prefix we will have that this point will lie on our boundary, we only consider the circles with this point on the boundary, and we proved that even this point lies on the boundary. Then to reconstruct the answer for this prefix, we will call our algorithm like F3 for this prefix and for both this point O1 and the current. And again, what does this algorithm? This algorithm takes the set of the points for which we are going to cover them, all of them by the circle. And we have 2 points that should be on the boundary. So we will initialize our circle obviously like the smallest contains both points. Like we will construct the circle with the diameter matching this segment, or 1 or 2. And we'll again trying to put all the points from our prefix inside our circle. If it goes inside, then well, we are still keeping this circle as the optimal answer. And if it again appears that the point is outside the circle, we can use like the same method to prove that the optimal answer for all set of points we've already here have inside, and this point, the answer should have this point on the boundary. And still since we know that we want to construct the circle that has this point on its boundary, and we only care about the circle that has these both points on the boundary, there's only like one way to construct this circle. So instead of this circle, we just remake the new circle, something like this. And we say that it is the only possible answer for us, and we will just keep it as a current answer. And again, just at this layer of the algorithm, once we have the point that is not going inside the circle, we can just reconstruct the circle immediately, since we proved that the point should lie on the boundary, and we only care about circles that has the pair of points on the boundary. And of course, when we are proving that the new point should lie on the boundary, we're applying to our proof this method with the translating the circles only among the circles which contains these 2 points on its boundary. So it's like additional restrictions that always should be held in over our smaller proofs. So once we prove that this point should be on the boundary, and we only care about only care about the circles with this pair of points on the boundary, then we can just reconstruct the circle immediately, since we already proved that that's the only way how we can cover all the points. So we know that this layer of the algorithm is just very simple. It just checks if the point does not goes inside, we'll reconstruct in the circle, and that's all. So this will clearly work in like size of the p time. And for all others, we'll just calculate the syntax a little bit later. Now let me just leave like this very simple code with algorithm. So it is so small, so I would even like to write it down. So if we have if you want to implement this method, so we will define our current circle, let's say C, and the smallest circle that covers set O, which is set which is if it's empty, so it's any empty circle. If it's 1 point, then it's circle of radius 0. If it's 2 points, then it's just circle on the diameter of the segment. And of course, if it's 3, so it's also like on a unique way you can intersect some I'm going to intersect these 2 things to find the center of the circle. That's how you construct it, if you forgot. And after that, you are going through all points and current set. So you put in if, let me check, like if C contains P, then just go and everything just great. We have our optimal answer contains the next point, which means that it remains the optimal answer. And if it is not containing, then we have to update our circle C with the result of the algorithm for the prefix. Since here we always have wanted to keep conditions that we keep in the result for the prefix. So once we have that point does not go inside, we have to build everything for prefix so we can go further in this layer of the algorithm. So we are reconstructing only for prefix and for our set of points that should be on the boundary, like with union with the current point P. And that's all. To that we return C. That's the whole algorithm. And the only thing that should be unclear for now is asymptotics. So let's try to calculate what would be the asymptotics. So of course, first I should say that we are going to calculate the estimated time, because here every time, like when we have this call of the function, we will reshuffle our points. So, and after that we'll estimate the expected time, because it does not obviously like work for all cases. This algorithm will have the good time. This algorithm only good because it has a good estimation for expected time. So let's try to somehow estimate the expected time. So we obviously wanted to estimate time like for F, like let's say F0. By this index I will just say what is the size of our algorithms of our set O. So we want to estimate this. And let me, instead of the point, just leave its size, because it only depends on the size, of course. So for this one, if we have that 3 points on the boundary, it just works in constant time, because this layer is kind of just reconstructs our circle. Here I forgot to add, like, if the size of the O is 3, then we just return, because there is no other way to have a circle that should contain 3 points on the boundary. And for this one, what does this do? It just checks the circle, trying to put one more point. If it goes inside, then continues. If it does not go inside, calls the method which works in constant time. So clearly, this one works in linear time. Right? Of course, here is just. But I will not write like this. I will keep it like this. So it's just n, maybe some constant, like it doesn't matter which exactly. Let's call it C2, like with the same index. Some constant, doesn't matter which one. And what about this one? So this already have like 1 point on the boundary, and when we're having the call of the F2, so here it will be just right here. Here it will be the sum of the calls. Maybe it better should be better if I put it not F, because by F I define the name of the method. Here it will, let's call it T. T is the time for the corresponding algorithm. So let's write down T1 as a sum of course, it will be calls of T2 of the size of the prefix, and here is like a probability, like that the point number I is not inside the answer for the prefix of like size I. So again, P I is the probability then that the last point index I is not inside of the optimal answer of the size I minus 1 of this one. So let's try to estimate what is this probability. So imagine we have like this prefix of size I. What is the probability that this point is not inside the answer for this? Let's a little bit change the statement. If we know that this point is not inside the answer for this prefix, we kind of proved before that it lies on the boundary of the answer for all prefix. So here we can say that this probability is that point I, the last one with the largest index, is on the boundary of our circle. And let's just suppose that there is no case where there is more than 3 points on the circle. So our circle can always contain 3 maximum points on its boundary. Again, we are not now considering that there is ever a case where more than 3 point appears on the boundary. Now let's say that it's only 3 at maximum. So this means that this is the probability that this point lies on the boundary. So this is one from the 3 points that should be on the boundary. And see if we have like, so obviously the order of points does not influence our answer. At least it does not influence the fact that this point will be on the boundary of the circle. And the chances, like, so not like this. So if you consider this set, just all prefix, there is 3 points on the boundary of our circle. And for this exactly layer, we have that one point is already fixed. So on this prefix, there will be just 2 more points that will define what would be the circle for this set. And since like the order of the points does not influence what these points exactly are, so that is just fixed some fixed pair of points, and it could appear in any position just because we have reshuffled all the points in the beginning. So actually the chances that one of the defining points would be in the last position is just 2 divided by the size of this prefix. So here we can replace this probability with 2 divided by I, and we can replace this time by C2 multiplied by I. So here we can reduce this formula, and we have like this sum is just n multiplied by 2 multiplied by C2. So it is again just n multiplied by some constant. And in a similar way, here we can estimate the expected time for this layer. It will be just or again this the same thing with probability multiplied by t1 from I, but here we can just in the same way prove that there will, for each prefix, it will be like always 3 defining points, and the order does not influence what the points are, and the chances is like for each prefix we can independently say that chances that the last point in this subset is defining just 3 divided by I. So like this, and this we are replacing like n I multiplied by C1, which will be just 3 n for C1. So it's again just some constant multiplied by n. And again, just to make the proof that there's only like 3 defining points, and they are so as I said, we're supposing that there are never 4 points on the circle, but even if there would be like 4 points, then we actually don't care if the points will be like more than 3, will be like 4. So in this case, we will just get the correct circle for sure before the last element, if it's even one of the defining elements, and it is the last one. We still will have no reconstruction in this case, because we would have this circle already constructed by some defining circles without even this one. So in this case, if this point is on the boundary of the circle, and there were at least 3 points on the same circle, we would have this circle even previously. So in this case, we would not call the reconstruction of circle. So we only call the reconstruction where there are exactly 3 points on the circle, and the chances that the last point is this defining circle, they are like decreasing with the size of the prefix. Like in if you use the formulas, the size is reduces with the time of the that just requires to reconstruct the answer for this prefix, and we just get that the expectation of time for the whole algorithm is just linear. I know that there are some tough things in this algorithm, so even if you like imagine all this translation of the circles, it is still like you have to understand that when we have some points lying here in our call, this means that we somewhere previously proved that we all for sure have to get these points on our circle, and we only care about the circles which contain this point. And now we don't care about why, because we proved it on the previous layer. So this algorithm should like only consider the circles that contains these points on its boundary, and after that looking for just the current circle, trying to maybe increase it, and if we increase, then we just additionally prove for some point along with all the points that we already have to use, like points on the boundary. And once we are proving that the point should go like on the boundary, we just call another method which like believes that we only need to consider the circles with this point on the boundary and only consider this kind of circles. So it's kind of like a distribution of responsibility. So one of the layers proves that we only have to consider these circles, and the next layer only consider like these circles without like thinking about why do we have these points on the circle and why can we just try something else. It just believes that all these points should be on the boundary. I think I'll try to find a problem where you can try to submit the solution if you would like. I think we are going to the end of today's lecture. If you think that you want to ask a question, please go ahead. So anyway, you can ask me anything personally, and for the ones who will not have any questions, see you on the contests. Today probably will be a slight harder contest than usual. Maybe. So let's see how you would like it.